Section 2.1 continued. Day 2 of quadratic functions here. Now you're going to be given different pieces of information about the quadratic function. You're going to be asked to take that information and go ahead and write the equation. Remember our standard form that we talked about for a quadratic equation is f of x minus k equals a times x minus h squared. So there's really only two things I need to know to be able to write the equation. I need to know the vertex. That will give me h and k. And I need to know this value of a. That's our lead coefficient. Other than that, that's the only information we have to have. Vertex we're given directly. So there's our value of h. There's our value of k. Let's go ahead and plug that in. F of x plus 2 equals a times x minus 1 squared. The other piece of information we're given is that our parabola or quadratic function passes through the point 3, 6. Sometimes in the homework, you will see it written like this, that it passes through a certain point. Sometimes it will call that point a solution point. All of it means the same thing, so don't get confused if you see it written a different way. In this case, remember if it's a point on the graph, that's an x value, and a y value that we know is a solution. So let's go ahead and plug in 6 for y, plug in 3 for x, and simplify. 8 equals a times 2 squared, which is 4, divide by 4. We get a to be 2. We now know a, we know the vertex. Go ahead and write your equation. F of x plus 2 equals 2 times x minus 1 squared. Write the equation of the quadratic function given the following information. This time it passes through the points -1, 0, and 3, 0. And we want one opening up and one opening down. In other words, there is not a single solution to a parabola that passes through these 2 points. To do this problem, you have to make the connection that we talked about, that x-intercepts are the same thing as solutions to the quadratic equation. So I'm going to do something off to the side here that doesn't directly relate to the numbers in this problem, but will help you understand what we're doing. If I ask you to solve this equation, what would you do? Well, you would either factor it or use the quadratic formula. If it's factorable, obviously it's a little bit quicker. This is factorable. X plus 9, x plus 1. Set each of those factors equal to 0, and you get x equals -9 and 1. Which also means that if we looked at the graph of this, that the x-intercepts would be at -9, 0 and at 1, 0. Those x-intercepts are precisely what we are given in this problem. So basically what we need to do is we need to take this process that we just did, and we need to work it up backwards to get to our quadratic equation. Well, this solution of -9 right here is produced by the factor x plus 9. This solution of 1 right here, that should be -1. Go back and fix that. That solution of -1 is produced by this factor right here of x plus 1. So if I know the x-intercepts, remember we also know the real solutions. So our function over here, what factor is going to produce a solution of -1? That's x plus 1. What function is going to produce a solution of 3? That's x minus 3. And now all we need to do is FOIL this out. We get f of x equals x squared minus 2x minus 3. So there's one equation that would have those two x-intercepts. What direction is this opening? Well, that's opening up. The reason we know it's opening up is because the coefficient on the squared term is positive. Now we need a second one that opens down. Well, how can we be guaranteed that we have the same exact solutions, but it's opening down? Put a negative on the entire function There's our second function. That one now opens down. The daily cost for manufacturing a product is given by that cost equation, where X is the number of products produced each day. How many units should be produced to minimize cost? Okay, a couple of questions preliminary to do in this problem. If we have a parabola that is opening up, does that parabola have a minimum value or a maximum value? It has a minimum value right there at the vertex. If it is a parabola opening down, does a parabola opening down have a minimum value or a maximum value? Has a maximum value again at the vertex. So regardless of whether we're talking about a minimum or maximum, they're both always at the vertex of the parabola. It's a minimum if it happens to be opening up, a maximum if it happens to be opening down. So in this case, all we need to do is take this equation and complete the square on it to identify where the vertex is. We'll know once we get it into standard form whether it's opening up or down. Therefore, whether it's going to be a min or a max, it actually tells us that it's going to be a minimum cost. So that means it should be opening up at the end. If it's not, we know we've done something wrong. So go to your original equation. Get it set up to complete the square. To get this set up to complete the square, we need to move the constant over first. So subtract the 1200. Then we also need to factor out the 0.1. So we have x squared minus 70x. 0.1, if I distribute that back through, times 70 does equal 7. That's how we know that's how that factors when we take the 0.1 out. It's now set up to complete the square. Take half the middle term. Half of negative 70 is negative 35. Negative 35 squared is 1225. To the other side, I need to add 0.1 times 1225, which is 122.5. We get C of x minus 1077.5 equals 0.1 times x minus 35 squared. There's standard form. From standard form, we should be able to identify everything we need to answer this question. First of all, we can see that it's opening up, so that means it will have a minimum. The vertex of this parabola is at the ordered pair 35, comma 1077.5. So what does that mean in the context? How many units should be produced to minimize cost? We should produce 35 units, that's our x variable, at a cost of $1,077.50.